last time we talked about the algorithm. So the algorithm I talked about it is about offline algorithm, one-line algorithm. In a later discussion, we will focus at the offline algorithm, okay? So that you can understand what will happen. The online algorithm is just, how can I say? Well, it depends on the algorithm. Once you know the algorithm, then you know that no matter it's online or offline, we will do the same treatment over it, okay? So let's focus on offline in a while. Then we will try to use these tools, okay, these two guys, the available time and the CPU requirement, and we treat this CPU requirement as time. Once it is on the CPU, let's say every time we have a time unit, let's say the 5 time units, after the 5 time units is gone, that particular process will be killed, okay? And next is the output, okay? We focus on these guys. Before we start last time, we talked about what is turnaround time, what is waiting time. So come back to the parking shop example. So the turnaround time is the time that you enter the shop and then you come out. So it's turnaround time. But during the turnaround time, you actually get different service, right? The service may be from the cashier. The cashier help you to check out all the things, okay? And also you go to shopping, but you also have waiting time. That is the time that you can look at any service. You can do the shopping, you queuing up without any purpose, waiting for the cashier to be idle, and then you can pick it, okay? And you can model that parking shop as we call it a single queue multi-processor environment. Okay, so we have at least 2 processors, sometimes 3. Okay, so there's a waiting time. You are not happy about it. Here is the time that you have to wait. Now, we go to the algorithm. Okay, so the algorithm deals of the algorithms here. Okay, you cannot find a particular one will appear only in one operating system. Usually, an operating system can have multiple of it. Okay, let's take the FIFO for example. FIFO scheduler means first in, first out, right? Who come first will execute first. Actually, it's implemented, okay, in Linux in one of the priority class. Some very high priority process want to take the CPU for some time, so he will just jump into queue and become the head of the queue and start executing. The next guy is the source top first. Later on, I will tell you where it exists or not. This exists everywhere. I don't know whether you have learned the router architecture. Okay, if you have learned router architecture, this round robin key, the term here also appear in router scheduler. Router scheduler means it's want to route so many socket. Okay, I don't know which socket to route. Okay, so it will take a round robin style. Round robin means I will have let's say n guys. I will pick the first guy for some time, second, third, and then go to the n guy. After I schedule all n guys, I will go back to 1, 2, 3, 4, 5, and then go to n, 1, 2, 3, 4, 5, and then go to n, okay? So this round robin is also implemented in router if you have learned, what is that? The fairness stuff over the router things, okay? It's called deficit round robin, something like that, okay? I remember this because I teach CS version. Okay. So the priority scheduling means that you enforce some rules so that a particular process has a definite advantage over another. So what is the definition of definite advantage? It's not by time, let's say in the previous time, okay, I take the advantage. Outside that time, I don't take it. No, okay. Priority scheduling means that once you exist of a higher priority, you will always gain something. And later on, I will talk about how is gain that extra CPU resources. Okay, we always talk about CPU resource. Last is we have a double criteria here. So I need a pen. So double criteria is first of all, you see the priority keyword. Okay. So I implemented some queues here. So maybe this queue is a higher priority, this queue is lower priority. So the 2 queues will go to the same CPU. Okay. So whether you choose a particular queue or not is based on the priority, and within that particular queue is its own algorithm. Maybe this queue is FIFO, this queue is another, let's say the SJF, okay, the second one. Okay. So let's take a look at FIFO. FIFO is mostly easiest guide to understand. Okay, it is the one that you use in parking shop. You go to McDonald's, KFC. They all having a FIFO. Okay, but different store implement different ways. Okay, like McDonald's is multiple queue, multiple processor. Okay, and you cannot split the monitor. You understand what I mean? You join this queue, you can jump to another processor. Okay, but let's say in a case for parking shop or as well as KFC, you can go there and take a look. Single queue, multi-processor. Okay, so you will join only one queue and get service from any one of the processor. And while you're executing over one processor, you cannot jump to another one. Okay, so this is not in the case for computer. Okay, computer is a different things. You may have multiple processor and maybe you have multiple queues. Let's reduce the case into single processor, single queue. Okay, so single processor, single queue means that you are in the queue and there is only one guy can serve you. Okay, what's the meaning of serving you? Because it's the FIFO queue. I will guarantee that based on this arrival pattern. So what is the previous arrival pattern? Is 0 time is first guy. So this P1 arrive first, and then P2, and then P3. Based on this, you already have a queue, right? So this guy is the head of the queue, this guy second one, this guy third one. Now when this guy is occupying the CPU, it won't go away. Okay, so this is one of the criteria, and it is also the same thing for your parking shop example, right? You queue, you get a service now, you won't go away, right? Until you finish the entire transaction, then you go away. Okay, so this FIFO is also having these properties. Okay, and when you look at this queue, okay, it doesn't mean anything, right? Because it's being controlled by this arrival pattern. So who arrive first will be in the head of the queue, and based on this, actually we can compute something. So one of the things that we want to compute, first of all, we want to compute the turnaround time. Okay, so turnaround is here. Okay, maybe you go with turnaround time first. Turnaround time means that you enter the shop, and then the time that you leave the shop, you start let's say that you enter the shop as this guy, time 0. Then you can leave the shop after 24 time unit, so your turnaround time is 24. Then how about the P2? P2 is a little bit hard, right? Because this guy is having a hard time. The one before it is having a very big transaction. Okay, you can imagine that if you have go to go to a KFC, okay, or a parking shop, okay, the one stand before you is from what is that? The hostel society. They usually buy cars of things, okay. Or you go to KFC, that guy before you buy buckets, okay. Then you will be very unhappy, okay. Because why? Let's take a look at these two numbers. First of all, the time that you have to stay in the shop is longer. Okay, so you have arrival time 1, and then you have to wait until P1 finish, and then you can leave. And at the same time, you are waiting for the service without doing anything useful. So the waiting time is also very big. Now, how about you can check against using your print out the notes. Okay, so how about we change something? Let's say there is a shop manager. Okay. When someone comes to the shop, okay, that guy will inspect how many items you buy, okay. Let's say if you buy the number of items is quite few, I will give you a higher priority and go to the earlier position in the queue. Let's say we do this. These two guys are having the same CPU requirement as if they buy fewer things. So the shop manager decided, yeah, I put you in the front of the queue. Instead, this guy, I modify it manually, modify the arrival time to put you later so that when you enter the shop, you are at the end of the queue. Although originally is the first guy, okay, I modified it. Let's imagine we can do this. Okay, so what can you say about the entire system performance? It's a lot better. Let's take a look at how unhappy these two guys are. What are the times that they are unhappy? They have to stay in the queue without being serviced. Now for P3, the time that is stay unhappy is 0 because one is entered the queue, it gets the service. Now how about this guy? This guy is also quite happy, or I should say happier than the last time. Last time he has to wait until P1 finish that huge transaction and get his turn. Now this time is wait for fewer time. Only 3, but it's not 3 by the computation because it's arrived later, arrived at time 1. So time 1 minus 3 is 2, so it's wait for 2 seconds plus 3 more seconds, then 5 seconds, then this guy can leave the shop. So in the entire throughput, okay, you can do a calculation. This throughput means that average unhappiness is 2. Previous case, average unhappiness is 16. All right. So what can you say about this? What can you say about this? It seems that if we are doing offline scheduling, okay? So let's say that the parking shop run like this, okay? Everyone go into the shop. You don't need to queue up, okay? You just register your number of items to the shop manager, and the shop manager will do his own scheduling for you, okay? So you don't need to queue. So what is the throughput if the manager is smart enough? Okay, it can produce a throughput that minimize your happiness, or well, it depends, right? It can also minimize the time that you stay inside the shop. Okay, so this is the motivation of the next algorithm. The next algorithm is, this is the thing that I just said. Okay, so sort the job first. Okay. So what is sort job first? Okay. Well, I guess you face this every day once you enter the university. Okay. So you have many assignments. Okay. And their deadlines you actually don't care, right? You just know that you have assignments. So what is the assignment that you will pick to do first? Usually it's the easiest, and you predict that the time that it needs will be shortest. Then you do this first. Right? It seems that you will get happier. I finished one, okay? Yeah, actually, yeah, the CPU requirement that you estimate will drop. Okay, it's always like that. You're estimating, that take 2 hours, and eventually become 2 days. Okay? So this is the sort job first, and you usually implement it. But in a real scenario, I already say that you cannot make a perfect estimation, and it's also for the computer world. Okay, so it's out of date because people find that it's not going to work. Usually your estimation is wrong, okay, but it exists for some time in a mainframe time, okay. So this is the source code first. The source code first is have 2 versions, okay. And why I give you 2 versions? Because I want to bring about a concept called preemptive scheduling, okay. So let's take a look at the version number 1. We call it non-preemptive scheduling. So non-preemptive means that an arrival of a new job won't stop the original job and kickstart the scheduler to pick another one. So that means that once you're in the CPU executing, let's say this P1 is 7 seconds time requirement, then no matter how many people get into the queue, it won't preempt it. Okay? But usually the world is not like this, right? Imagine back to your assignment scenario, okay? You only have one assignment, okay? So you doing that assignment. I don't know whether you're doing that, okay? So then suddenly another assignment comes. Usually it's preemptive, okay? It will preempt your original assignment, and you have to take a look whether that assignment is worth doing, okay? And if it's not worth doing, or it's take too long, okay? Then I keep on doing the original one, okay? So that is the preemptive version. And for the non-preemptive version, so you are very confident that you can finish it, okay? So you will keep on doing it, ignoring the remaining guys. So at the time 7, I will finish all job, but at the same time, these 3 guys already come because arrival time is 2, 4, 5. So this 3, 5 comes, then you will have 3 assignments on your hand. You do an estimation. The estimation is, this assignment P3, okay, supposed to be the shortest one. Then you start doing it and spend 1 second for CPU case, okay, and finish it. So you will keep on doing this and pick the smallest the CPU requirement, but this time there is I here. So choose the same as, let's choose a lousy way to break the ties is use the order of its arrival. So P2 arrived earlier, so I KO P2 and then eventually P4. Okay? So the number is not important, okay, because you don't have any contrast. I set up a new scenario, you cannot contrast this to FIFO. So what I'm going to contrast with will be the preemptive version. Okay? So whether you think that, okay, you can make a guess, or you just take a look at the notes, okay? Make a guess. You focus at all the assignment, you start with one assignment and you keep on focus on that. And then you finish the assignment, and then the remaining set of assignments, you choose the short stop first and continue with this schedule. Is it good, better than the preemptive version that you are doing one assignment and suddenly another professor gives you an assignment? You take a look at the assignment, whether the assignment is shorter than the one that you are working with. If yes, it's the shortest among these two, okay, the shorter one, then you pick that guy and start running over the new assignment, but put the old assignment aside. And after the new assignment finished, say that there is no other preemption there, then you go back to the old assignment. Is it better or make you happier if you're doing the non-preemptive version or preemptive version? You can big guess, okay? We go on. So the preemptive versions comes. So the preemptive version, we have to set up a requirement. The requirement is about how to do a preemption. Okay? So the preemption means that the time that when a new process arrives at the system, then we will push the original one and imagine that there is a scheduler. The scheduler is a human. Okay? We'll step forward and choose, which one has a shortest, okay? Shortest CPU requirement that I pick the guy up and execute it, okay? So this is the preemption rule. Now let's go. Same scenario. So at time 0, we only have one guy in the system, so I don't have any choices. I will choose P1, but when the time comes at the time equal to 2, okay? So we have to make choice. With time equal to 2, so this guy will have a remaining CPU requirement down to 5. But how about the new guy? The new guy is more, a need shorter requirement than P1, so I will schedule P2. But the good thing is this is long last. Another preemption will come eventually at time equal to 4. Okay? So when the preemption comes again, we will take a look at this column, 5 to 1. So this guy is 1, so I will put P3 to run. And it so happened that we would have two events happen together at time equal to 5. The first event is, of course, time equal to 5, there is a guy coming in, there's a P4. And another event is, this P3 dies. Okay? So two events happen together, and of course, we don't need to care about this guy's already gone. So I take a look at this column and choose the shortest guy to run. It's supposed to be P2. So I will run P2 until it dies, then continue with the schedule, and we will have this schedule like this. Okay? Now the ordering is doesn't make any difference. Okay? Because you can take a look, the finishing time doesn't change. I don't incur extra penalty. It's still 16 compared to the previous case. Also 16. Now, what is the happiness calculations? Okay, so I have a contrast here. The non-preemptive version, that means you don't care about the new arrival. Okay, no matter what is coming, I will keep on doing the assignment that on my head. Okay, so you will have waiting time, your average unhappiness, okay? The average unhappiness is based on the assignments, okay? It's kind of strange, okay? Let's consider it as an unhappiness index, okay? Unhappiness index. And the average finish time of the assignment will be 8. But if you go to have a preemptive version, actually you have a better performance. on average, you are happier, okay? Because it seems that I've received a very short assignment. Let me kill it first, okay? It's very human, right? Very just like you guys, okay? Someone gives you a very easy assignment, you do it first, okay? Ignore the OS assignment, huh? Okay? Then how about the turnaround time? Turnaround time is of course better because let's say there is assignments very short time. You don't put it into wait and immediately finish it, okay? So yeah, you will have a shorter turnaround time on average, okay? But there are some exchange. There are context switching, okay? So in a CPU or scheduling scenario, that means that you have to load process back and forth for 2 more times, okay? And the real scenario is just another case like you're switching from one assignment to another assignment. Usually it's not that smooth, okay? I also always had the experience when you switch from one job to another job, then in between it will be Facebook, YouTube, whatever, and then you finally jump to that assignment, okay? It's usually like that, okay? So I would consider the real life context switching is more costly, okay? So, but in terms of scheduling performance, this is the best, okay? Even better than the non-preemptive version. Of course, needless to say over the FIFO. FIFO purely depends on the arrival pattern. If arrival pattern is just like SJF, then you will have SJF performance. If it is not like SJF, okay, then you have a very bad performance. And also one more thing, FIFO is always non-preemptive. You won't have FIFO which is preemptive, okay? You will hate this, okay? You can imagine the case that you go to a company job, you are going FIFO, but it's preemptive. Then what will happen? Yeah, it's just going to become a stack, okay? The one that you come later will get first, okay? Yeah, it's just become very stupid, okay? So this is about performance. These two are performance-oriented scheduler. Why we have this kind of scheduler is because of the old days, okay? The old days when the universities, the banks buy computers for one or two, okay, requirement, okay, for the universities for scientific computation back in the 1960s, 1970s. The banks, okay, they may want to do some sorting, okay, sorting who has highest account balance, okay, who is in debt, okay, having negative account balance, okay, so they are looking for performance. But nowadays, you don't care about performance, okay? What does the meaning of don't care about performance, okay? Let's say you're loading a PDF file, and at the same time, you have, now it's not MSN, okay, WhatsApp, okay, WhatsApp web version, okay, a message coming in, okay? Yeah, do you really count together with the message and I have a handout, I have a Gmail, okay, I have a game, okay, and doing all the calculation of waiting time and turnaround time? You actually don't care, okay? What you care about is interactiveness. So what is the meaning of interactiveness? It's about the round robin scheduler. Okay, so I consider it as a modern implementation, but it's not modern enough. Let's take a look what is it. Okay, so there's a piece of words here. Okay, it's for you to revise the notes. Okay, the red guys are the important guys. First of all, what is round robin? Round robin means that I already told you I have n jobs. Okay, I will schedule the first one, second one until I schedule the n one. Then I will go back to 1 and 2 and 3 and 4 and then go to n. Okay, it's as if there's a queue there. There's a queue, so that I have order 1, 2, 3, 4 up to n. Now, what is the meaning of running 1 and then 2 and then 3 and then 4? What is the meaning of that and then? That and then is actually means there is a pointer, or in the scheduling world, we don't call it pointer, we call it quantum. Okay, pro is quantum. Okay. Quantum. It's a pointer in our normal sense. Okay, so the scheduling we call it quantum. I will switch to quantum now. You have quantums for every jobs that get birth. Okay, so let's say every jobs get birth have a finite quantum. Let's say 2 milliseconds. Okay, so when your pointer or quantum has used up, then you have to leave the CPU and let the next guy to run. And that is the moment that I have the first process run, and then go to the second one, and why I go to the second one? Because the first one quotas will stop. Go to second, go to third, and eventually I go to the last one. And what happens if I go to the last one? It means that all the ones that before the end has used up their quantum. Okay? So it is the moment that entire queue has claimed or has been scanned for once, okay? Then you will recharge the entire queue to come back. And imagine the case that the pointer means a bunch of quantum, okay? The pointer is small enough. Let's say every process receives only 2 milliseconds. So what is the aggregate result? The aggregate result is a lot of context switching, but you will have a feeling that every process run in parallel. Yeah, imagine it's like this. Every process goes to the CPU for 2 milliseconds. And the switch, let's say the switch between one and other is negatable. Then the illusion is every process run together. Okay, this is the illusion, okay? So let's take a look at the scheduling. So the scheduling is, I copied the old configuration from the SJF, okay? So I set up some criteria. So I have 2 time units for the pointer or quantum of that process. When it uses up, okay, it becomes 0, then you cannot schedule. And when every process becomes 0, it will recharge, okay? So, oh, by the way, this implementation, I am not just creating stories, okay? This implementation is really implemented in previous Linux kernel 2.4, okay? So nowadays is what is that? 4.0 series, okay? So previously is 3.0 series, and more previously is 2.6, and then 2.4. 2.4 is around when? Around 2005 to 2006, something like that, okay? So it's 10 years before. 10 years before, the Linux kernel is really implementing this quantum usage and recharge scheme. Every process uses up their quota, recharge. So that scheduler is not very good, okay? Because it has to wait everyone to use it out and do a scan whether you have used up or not, okay? So it's that's why the scheduler by that time has a name. We call it big of n scheduler, okay? You have to scan all n processes in order to determine you have to recharge or whether that particular process should be running or not, okay? So let's go. How this big of n scheduler is being implemented. First, based on the arrival time, I have a circular queue here. Later on, you will see why I have this circular queue. The first guy execute first. It arrived at the system without any competitors. So it would run for 2 milliseconds or 2 time units, time 2 seconds, whatever. Okay. Then after 2, okay, so happened that I created a scenario to be 2. There is another event happen in the system. Another process just come in. Okay. And at the same time, this guy's quota or quantum has used up. So because the queue length is 2, and the entire queue, you do a scan, still there is a guy with some quantum left. So I don't recharge this guy, I will schedule this guy. And after 2, this guy will use up his quantum, and at the same time, one more process comes. So I will do scheduling like this. With this guy, these 2 guys use up their quantum. Now, this guy won't use 2 quantum, but only 1 because the CPU requirement is just 1, and then it dies. So I create the scenario. So at the same time, this guy dies and this guy comes in. So I still ignore these 2 guys. Okay, these 2 guys, I do a scan. Yeah, you have quantum 0, quantum 0. Oh, this guy is quantum 2. I pick this guy up and let the CPU to run it. Now I use up this guy's quantum, and we will have a scenario that I should have an animation, but this is a PDF. With PPT, I have an animation that I having all guys gray. Okay, so you can imagine that. Oh, there is a case that all guys are gray. Okay, so you do a scan. That's why I need a circular queue here. do a scan, and oh, all agrees. So what should you do? Using this circular queue again to recharge every process with their initial quantum 2 again. So after the scan again and come back, you start with this to schedule again, give it 2, and then yeah, this guy needs more, but this guy needs fewer. So this round will have finished the execution. This round also finish the execution, and goes on. So you will have this scenario that keeps spinning over this circular queue. And in the kernel of the 2.4, we really implement every processes as a circular queue, and there is a for loop to loop through the entire queue to see whether you have used a quantum or not. Okay? So, and it is the end. Okay? So the number isn't important as long as you don't have any comparison. Let's go to comparison. So the comparison is, yeah, very bad. Our are all champion for the worst performance. The most unhappy scheduler, the time that you stay inside the system for the longest time, turnaround time. And the most number of context switching. Okay? So why bother? Why we need this implementation? And I said, nowadays, the modern operating system is talking about interactiveness. I want a system that I can have a feel that every process run together. Yeah, this check with your phone, your iPhone, your Android, they are all using this way. You won't expect that there is an app running, and that app running, then all the guys in the background cannot run. You won't expect that, right? You will expect that while you're playing the game, you can still receive your notification. You will still have there's an alarm clock maybe, okay, or Messenger, your WhatsApp, okay, will run in the background. So this is the implementation inside the kernel so that it supports multiple processes run together and have an illusion that they will receive enough CPU resources so that you won't feel that it's being frozen. Yeah, you can imagine that what happens if I have a bigger quantum. Let's say every process, you invent a new scheduler and let every process have a quantum of 1 second of real time. Then you can imagine what happened to your system. If it's 1 second, what will happen? That gives you a number. 1 second for each process, you have 1,000 processes. Then what will happen? For one round of our scheduling, let all processes use up their quantum. You have 1,000 processes. For one process to receive the next round of CPU attention will be 1,000 seconds later. Right? Is that not 1,999, okay? 999, okay? You go one round and everyone spend 1 second, and come back. It's 999 seconds later. Do you want the system? No. That means that, yeah, you can check your WhatsApp every 1,000 seconds. Okay, then again, oh, WhatsApp come back. Oh, okay, yeah, treasure that 1 second. Okay, you have that 1 second only. Okay, and while we're thinking, oh, let's go to another process. Okay, will you use that Windows or use that phone? No, you won't use that. Okay, so this RR is confirmed to be a good one as long as you have more and more context switching. Okay, you have a lot of context switching, then it will give you an illusion that every process run together, but there are other penalties like the context switching is actually not irregularable. You incur times, okay? Or this RR is actually being fair. Yeah, you can have a sense that it's being fair, right? Every people receive the same amount of quantum, and everybody will be waiting approximately for the same time for another round of scheduling. So it's as if they are fair and also have the same waiting time for everyone to have the next schedule. So what is the meaning? Let's say let's say your process is in a queue like this, okay, 3 guys. your process only need 1 second to finish, okay? But these two guys also need 1 second, So for the worst case, how many seconds this process will need to be finished executing? For the worst cases, let's say, I don't know why, the scheduler chooses this guy first. Okay, and this guy 1.1 seconds, this guy 1.1 seconds, and then KO, and now this is your turn. So the worst case is you wait for 2 seconds, and then execute for 1 more second. Of course, that 1 second is a random number. Okay, maybe it is a fewer time, but the RR doesn't guarantee for performance. It's only guaranteed for interactiveness, so that every process run together fairly. Okay? So yeah, this is the worst that I've just talked about. Okay, and the joke I also talk about is about the time that you spend really 1 second for every processes. Okay, and then you will have a frozen from time to time. Okay. So, any problem, any question you want to ask, okay, or any scenario that you want to discuss with me, okay, or some things that you use your operating system and you don't understand. No, okay, good. Yeah. Also, another observation is fair to all processes. Okay. By the way, some points that was worth discussing. Okay. So, what is the fair treatment between the CPU and I/O here? Does it reflect it in RR? Actually, RR scheduler don't care about I/O bound process. Your I/O bound process, you go to wait for I/O, and whether you will receive some bonus treatment like, oh, you didn't go to the CPU, okay, for some time, I give you some bonus, okay. Now, in the previous implementation, I didn't say anything about this, okay. So it depends on different system, okay. During the break, I have to find one figure, okay. I scan a figure from a book, okay. That book is talking about Windows Vista implementation. Windows Vista kernel implementation, and it's written by Microsoft. Okay, that book tells you one thing: that our scheduler inside the Vista actually pay attention to this guy. Pay attention to what? The fair scheduling between CPU bound process and IO bound process. When the IO bound process has been wait for something, when it comes back to the system, give him bonus. For what? Later on, I will capture that screen, okay? Okay, another thing is, instead of bonus, okay, is there anything that we can make it fair? What is the meaning of bonus? Let's say you have an LS program. LS program is sucks, okay? You won't enjoy having a bonus with a LS, okay? Let's change it, okay? Maybe a DVD playing software that access DVD should be slow, right? Then that bonus makes sense. If that process go to the device, get the data, and when we come back, it cannot play immediately, then what will you find? You will find the DVD playing process will be very laggy. Play for some time because you run out of your buffer, go to the disk, pull something back, but you cannot be scheduled immediately, then some laggy time, then play continuously. But how about the the scheduler aware of this? You are the IO bound process, okay, usually it's because of waiting for some data. Okay, when you come back, you're playing for this amount of time, now immediately schedule you when you come back. Then you will have a smooth playback, okay? And that's why Vista sucks. You see no one uses Vista anymore. And every people complains about Vista. It's because it's pay too much attention on the I/O. And when you really execute something, it's being jammed by order. You really jamming from a CPU bound process and penalize CPU bound process. I/O bound wins, always win. Okay. So let's take a break, and I find out that figure for you. I should have downloaded this. Can be explained together with the multiple queue priority scheduling. Okay, so we will make it together. So what is the priority scheduling? I can't remember which week. Okay, I demonstrate to you what is the nice command, right? Nice command. So what is the nice command? Nice command is a priority that is able to be changed. Okay, while you start the process, you can say nice, and that guy will decrease their priority. So we call it dynamic priority. You can change, you can upgrade it, you can downgrade it by using the nice command. Of course, you are the normal user, then you can always downgrade your process from a normal priority to lower priority. Okay, so what is the meaning of lower priority? The lower priority is that I give an illustration, very easy to understand. Okay. So one of the resources that you have, okay, is the quantum, right? Quantum. Or whether you can stay in the queue, okay? So whether stay in the queue. So the nice command is actually tackling this guy. Instead of tackling this guy. So what is the meaning of tackling this guy? If you say that you want to be a nice guy, then the quantum you receive every round of recharge will be smaller than the original default value. So if that is being reduced, so what can you expect? Let's say every round, every process can run for 2 milliseconds, but your process is only 1 millisecond. Okay? So now in the long run, what will happen? We will have a round by round scheduling, right? Every time you receive 2 milliseconds, I receive 1 millisecond. So in the long run, approximately you will receive 66% of the CPU resource, but I receive 33%. Right? You receive twice and I receive once. Okay? So this is the nice. Okay? Of course the rule is not that simple. It's not always 2 and 1, okay? Yeah, maybe originally it's 40. You change the nice value, okay? And I can make a fine granularity by decreasing 1, 2, 3, 4, so on and so forth. Okay? So this is what we call dynamic priority. Now another is something that you cannot discover. Let's take a look at a system. Oh yeah, after we put, I lost the virtual box. Okay, wait a moment. I have to restart my virtual box. Okay, so why I have to use virtual box instead of Count9? Okay, there's something that Count9 cannot show. Okay. Wait a moment, it's being launching. Hey, come on. Okay, good. So something that guy cannot launch is here. Yeah, you cannot see it. Okay. So there, yeah. Okay. Quick. Okay. So this column. Okay. This column has some numbers. What are the Ubuntu? Ubuntu is our login account. Okay. The account that you log in is called Ubuntu. So you are the normal user. So the normal priority, not nice. Okay. Ni is nice value. Okay. This is dynamic priority. This is the what we call the static priority. The static priority is by default you launch a process, you will get that by default, and you cannot change it unless you are the roots. So the roots can launch some very horrible process with this key, RT. We call it real-time processes. They have a supreme, really supreme, invincible basically, okay? Supreme invincible priority class. It will always wins against the numbers. No matter which number you are, when you are RT, you wins. Okay? So what is the meaning of you win? Let's take a look at this illustration. The illustration is like this. Okay? So let's say the the top guys, okay, are the priority with the higher number. This is the priority with a lower number. So the real-time or RT processes will be of this class. Will be of this class, the highest class. So what is the meaning of highest class? Let's say this is the configuration, and in a multiple queue environment, now this is a multiple queue environment, you have different queues, and different queues have different priorities. Once you launch an RT or real-time or high priority scheduler, this guy will execute first. I mean, this process, sorry, not scheduler, process. Execute this guy first. Until when? Until all the priority class 4 guys are gone. Okay, those guys cannot run. Until these 2 guys are gone. Okay, so let's say these 2 guys are gone, then will be for a chance for priority class number 3. And after 3 are all gone, then you can schedule 2. So that's why those RT process, the RT process you've seen here, why I have to take a look at the top and let it run for some time, and then suddenly I say, oh, it comes, okay? Because these RT guys are usually short-lived by default, by the design of the system. You cannot launch a real-time process that runs for an hour, okay? So if there is a, back to this figure, let's say this guy runs for an hour, what are the remaining processes that you create will be frozen. It just don't respond anything, no matter how hard you click the mouse, no matter how hard you hit the keyboard, okay? It won't respond because there is a very high priority process running, ignoring any other parts of the system, okay? So this is the problem, and that's why only the root is allowed to create real-time processes, because the root is supposed to be the guy that know how to control the system. Okay, so of course when I go to the next page, okay, the illustration continues. Let's say suddenly there is a very urgent jobs come in, and all urgent jobs usually have a real-time process priority, and it will take the CPU resource, okay, and usually it's preemptive, okay, because you can take a look at the names here. The names here seems to be very strange. Let's take a look at the process ID 10. Okay, so the process ID is so small. Okay, you think that it should be something important, right? Take a look at the name. The name is also very interesting. It's called watchdog. Okay, so why there's a dog running in a system? It's actually watching over the entire system to look for some blocking device, deadlock. Okay, deadlock later I will talk about it, okay, deadlock resources, okay, and this watchdog have to run whenever it finds some trouble, and that stop is not to bite, okay, is to kill guys, okay, kill some blocking processes. So let's say this watchdog come in, that means that there are some bad things happen inside our system, okay, so some migration guys, I don't know what is migration guy, okay, so let's go on. For another implementation, okay, so this is just an example I copied from some textbooks, okay. So from some textbooks, the textbooks say that there are some real very old implementation based on that textbook. This is the, how many of you have heard of Windows NT? No one. Windows NT, no one has heard, only you, okay. Do you know what is the meaning of NT? New technology, okay? Yeah, just like that, huh? Yeah, I start with thinking, oh, NT means new technology. So what is XP? XP is, you know what is XP? Based on that definition, it's not my definition, okay? So XP is like this, right? My definition of XP is this. Yeah, it's XP, right? Okay. Yeah, this NT is a new technology. Okay, so that is the scheduler of NT. So what's the NT schedulers look like? Okay, they have a very specially designed 2 layers of real-time processes. Okay, the first layer of real-time process is FIFO, non-preemptive, so as to guarantee some really important job can schedule, can run, and can finish without anyone can preempt it. Another is a sort of first. I already said that sort of first cannot exist, okay, but yeah, NT is an old technology, but it exists. Then for your normal job will be running as an hour scheduler, okay, with different queues of hour. Let's say you run out of the quantum. Is it running out of battery? Why? Hello. So let's say you have 10 time units at the start, and it is default place that you have a new process comes. So after the new process running for time unit of 10, you will drop to the next priority class. But after you drop it, of course you feel bad, right? Because others new guys or others priority guys higher than you will exist. But as a bonus, your quantum will be more. If you also use up the 20 units here, then you will drop to an even lower priority class. Okay? But you have a bigger bonus. Can you guess why they implemented it that way? Or what can you say about this performance of this scheduler? What is favored over this three class? Can you describe what happened if I have always create jobs which are short life? Then seems to be no effect, right? If all jobs are short life, then no problem. They all stay with priority class 3, one for a while and gone. Okay. Now, how about we have a mix of short life process and long life processes? Then what is aggregate effect? Okay, I will call this scheduler penalize the old guy. Okay, whenever your young process comes up, okay, you will have a high priority to execute first, so as to give you a very high response. Right? You just double click on something, and boom, it suddenly runs. Okay, because you have very high priority, and it's just an illusion. Okay, just give it illusion that it runs fast. Okay, you know Windows always being saying that it sucks. Okay, not responding. Yeah, it's trying to kill the problem. Okay, yeah, give you a high priority for new processes. Okay, but at the end, when process run for many hours, okay, they will just stuck at the lowest priority. Okay, and how about the entire system now is full of low priority guys? Then it will be the old scenario. It's always give priority to new guy, and new guy eventually drop to the first or lowest priority class. Okay, well, what happened? Okay. So this is the design of that book. Okay, claim that it's a Windows NT. I want to find the proof. I want to find out the Windows internal spokes on NT, but I cannot find it. Okay, so yeah, just believe in what I said. Okay, maybe what I said is wrong. Okay, so this is about the multiple queue priority scheduling in Windows. Now, how about in Linux? In Linux, the 10 years old big O N scheduler is implementing something like this. They have a mix of 100 priority classes. Okay, I don't know why they need so many. Okay, for me, if I'm an implementer of the kernel, I will always fire my job at 99 priority. Okay, yeah, but I don't know why they need so many. But there's some different priority scheduling classes. The other classes is actually the normal processes implemented as an RR queue. So there's an RR queue, but the name is others. Others are higher priority guys with red color. There is a mix of FIFO and RR. In Linux, they do the following. Okay, so I have animations. I cut it out. Okay, yeah, the animation I want to say that is about these two guys. Okay, what happens if the RR runs of the quantum? So it will jump to the end of the queue and let the FIFO to run. But FIFO don't leave the CPU. Okay, so the FIFO will jam the entire CPU until it's finished, then let the RR to run again. Okay. So, this is the end of this part. Okay. If you want to understand more over this class, let's say you want to run some processes with higher priority, you can take a look at this function. So, what is this function? It's called main page, okay, sketch, set, scheduler. Okay, so what is it? It set the priority policy, a scheduling policy, to change from sketch order to others, something that I didn't tell you, okay? To change from sketch order to batch to idle to FIFO to RR, okay? You can change by calling system call, but you have to be the root or you cannot call it, okay? Or if you are dare enough to take up the challenge, okay? Dare enough taking the challenge or what, okay? So this is really a big challenge, okay? And if you have enough time, you can go to edit class folder, okay? Take a look at assignment 1, okay? To implement an unfair scheduler, okay? And I have screenshots, okay? So let's take a look at the screenshots, okay? So I implement something called glue, okay? To glue these two processes. So these two processes running in a strange ratio. Can you see this guy pop up twice and this guy pop up once? Can you see this? 2 and 1, 2 and 1, 2 and 1. It's basically I modify the kernel so that it gives out this scheduling ratio. Okay? So this is the challenge, okay? If you want to know how to implement it, I know that you should be able to find some of our friends that have taken the class last semester. You can ask them for the source code, or you can download the specification here. Okay, it's just an advertisement here. All right. So summary is, well, we want to schedule something. We have 3 goals. Fairness, easy. Implement it as LR. It's by itself. As long as you give fair share of quantum, then you will have fairness automatically. Policy enforcement, we can solve it by priority scheduling. Okay? How about this balance? This balance, we didn't cover it, okay? But by the design of the DMA, last time we talked about DMA, I asked people how many of you know DMA. DMA allows hardware work parallelly while the scheduler or the CPU schedules something, the hardware moving data without your awareness. Like you want to load something to GPU, okay, let's say you compute something on GPU, you have to load the data. While you're loading the data, the system can do other things. I mean the CPU, okay? So by not scheduling something that working with the hardware, then you can already get this balance, okay? So these 3 goals are already solved. And maybe you are just puzzled, hey, after this is so many things about scheduling, you may have a questions. What is best scheduler? Yeah, what is best scheduler? It actually doesn't exist. Doesn't exist. In terms of theory, okay, theory is like, I don't know whether you have heard of it, okay, there's a scheduling class called NP-hard, okay? NP-hard means that if you want to have an optimized output, you need a non-polynomial time in order to look for that optimal output, okay? So from theory's sake, it's like this. From a practical point of view, actually, your requirement over operating system is very personal. Let's say my requirement is I want to run program very fast, but your requirement is you run your game very fast. Okay, it's totally different. Okay, so there is no scheduler can satisfy both needs. My way is I want to run my VM, I want to run my program, my simulation very fast. Then I need a scheduler favor CPU-bound processes. Like you want to play games, you want to have a fastest WhatsApp delivery, okay? Then it will be IO-bound processes as well as the RR scheduling, okay? So it's quite different. So you cannot say anything about it. And also there is some naughty guy like infinite loop program. How the scheduler knows that you are infinite program? No way, okay? So if the scheduler knows that you are an infinite program. That's good, okay? I know you're an infinite program. I penalize you. I don't schedule you for 1 hour, okay? To let others process have the room to run. But no way, we don't know. Actually, we don't know how long a particular program will stop, or you just don't stop. We don't know, okay? So there is no best, no standard. So the scheduling community is still evolving different versions of the scheduler. Okay, as I told you before, this 2.4 Linux kernel, the big O of N scheduler, is just 10 years old. Okay, 10 years before we have big O of N, and then we have the big O of 1 here. And some people say the big O of 1 is not good. Okay, then we switch to completely fair scheduler. Some people create that brain tooth scheduler. Okay, the BFS. Okay. So yeah, that is the way, okay? And nowadays, the scheduling community is looking at other ways to do the scheduling. Is they want to group something to schedule. They want to group, let's say that you are doing a DVD playback, okay? So I want to group the following. I want to group the screen display process. I want to group the DVD player. I want to group the hardware so that I can bring about a very good performance when you are working on this. And we call it process group or control group. Okay, so the community is still evolving, so I cannot say what is the best scheduler or what is the standard scheduler. Kind of standard is the RR. Okay,